Hey guys, welcome back to my YouTube channel. Myself Aratnak, and today I will present you to my new project. And this is what you are seeing right now. You are seeing a planetary ecosystem evolving inside my CPU. Here, every single fraction of a second, thousands of digital creatures are being born, hunting for food, fighting, mating, and as well as dying. So here's the crazy part. Every single one of them is connected by its own unique mutating neural points. And my computer is calculating all of these, the climate, the physics, the genetics, and the AI in just 0.35 milliseconds per frame. That's nearly 3000 simulation ticks every single second running on a standard RTX 4060 laptop. So as you can see here, it runs so fast in pure headless mode, dumping massive amounts of evolutionary data into CSV files. We can literally track how species genetics drift over time in response to a climate change. Most simulators struggle to handle just a few thousand entities before the framework tanks. So how is this so fast? It's because I completely bypassed the CPU. I wrote this entire engine from scratch in C++ and CUDA, expecting 100% of the logic directly on the graphics card. Let me show you the code. So in traditional simulations, you compute the logic on CPU and send data to the GPU just to draw it on the screen. But moving data across the PCIe bus is a massive bottleneck. In Genesis, the CPU is essentially unemployed. It just acts as a traffic cop, dispatching asynchronous commands to the GPU. Now, let's see the GPU one. To make this work, I had to write a custom memory allocator. I reserve a massive chunk of video RAM upfront. Everything is stored in a structure of arrays format. Instead of having an array of creature objects, I have one massive array of all X positions and one for all Y positions, one for energy, and so on. This ensures the CPU threads read memory they read in perfectly manner contiguous blocks, maximizing memory bandwidth. Now we'll go to the hardest part, custom neural networks. Now we'll go to the neural path. Here from neural, we'll go to neural forward. See you here. So now the hardest engineering challenge by far was the AI, as I wanted every creature to have a brain. Standard deep learning libraries like QBLAS are highly optimized for batched matrix multiplication, but they assume you are passing a bunch of data through the same network weights. Because this is an evolutionary simulator, every single creature has uniquely mutated genome. Therefore, every creature has unique neural network weights. Standard libraries couldn't handle this. So I wrote a custom CUDA GEMM kernel. Every GPU thread corresponds to one creature. The kernel decodes a creature 256 float genome directly into the network weights, pulls environmental data from its sensors, and evaluates from its specific brain topology. Because we do this across thousands of CUDA cores simultaneously, we evaluate hundreds of thousands of unique neural networks in just a millisecond. Now we will switch to the spatial hashing and ecosystem physics. Now let's show you a simulation here. As you can see here, this is a spatial hashing. So I just showed you how visually it works. But how do these creatures see each other? If 5000 creatures all loop through every other creature to find who is the closest, that's 25 million distance chunks per frame. That simulation would grind to a halt. To fix this, I implemented parallel spatial hashing. Every frame, a CUDA kernel maps each creature's coordinate to a grid cell and generates a hash. Then I use NVIDIA's Thrust library to perform a ridiculously fast parallel radix sort on those hashes. Once sorted, a creature only has to look at the memory indices of the creatures in exactly the same call as itself. collision detection becomes O of 1, constant time operation. So all of this happens entirely on CUDA streams. Now we'll go to the hardware realities and bottlenecks. Let me show you one visual here, the CPU bottleneck. So as you see the CPU bottleneck, when you program this close to the metal, you learn a lot about harsh realities of GPU hardware. It isn't magic. For instance, I had to fight wrap divergence in CUDA. Threads execute in groups of 32 called wrap. My genetic algorithm allows creatures to mutate different neural activation functions. Some use ReLU, some use tanh, but if creatures in the same wrap have different genes, the GPU can't run them simultaneously. It has to execute the ReLU creatures while the tanh creatures wait, and vice versa. It literally halves your compute efficiency. As you can see here, all the codes are here, from shaders to analytics, benchmark, climate. Each one has a code. I even model the ecosystem, and then the genetics, the fluid. This is the multi-GPU one, and for the wrap divergence, %50 efficiency loss. For neural, as I've said you, there's activation functions. In activation functions, there is ReLU, there's tanh, there's sigmoid, there's Swiss, there's spatial, as well as scenario, as well as rendering, and there's finally main.cu. Now let me show you the GitHub code. As you can see here, I uploaded my code to the GitHub. Now I'll show you the architecture diagram. This is a system architecture diagram, and this is a simulation loop flow chart. This is the memory architecture, PHR genome and neural architecture, SPH fluid dynamics pipeline, genetic algorithm GPU pipeline, climate system architecture, rendering pipeline architecture, analytics and phylogenetic engine, multi-GPU architecture, and there's performance context, what are the benchmarks conditions and known bottlenecks and hardware limitations. Here are the build instructions and usage scenarios, and running the tests too. Here are the few codes. So building Genesis pushed my understanding of C++ memory architecture and parallel computing further than any project I've ever worked on. It is incredibly satisfying to watch purely a mathematical system wield emergent lifelike behavior. I have built entire architecture from custom memory allocators to the genetic crossover kernels, completely open source. You can find the GitHub link in the description below. If you're a C++ nerd, a GPU enthusiast, or just love artificial life, check it out. Run the benchmarks on your own GPU and leave a star on the repo. Thank you.